Hey guys, it's Miss Johnson. I wanted to follow up our class discussion about distance graphs and speed graphs with a video that, in an organized manner, tells you what I was trying to say in fourth period or tells you what I didn't get to in fifth and sixth period. All right, let's go through it. I've got two scenarios here. One is where we have a distance graph and we want to get the speed from that graph. One of them is where we have a speed graph and we want to get the distance from that graph. Let's go ahead and start with the distance graph scenario. So we've got this graph, we've got meters on the y-axis, we've got seconds on the x-axis, and we've got our equation for distance, rate, and time solved for rate. Because we want the speed, we want the rate, I went ahead and solved for that variable. Cool. So now we're going to take a section of the graph we want to talk about. Let's take the first 3 seconds of our walk and figure out what rate we were going at. Okay, so the rate for the first 3 seconds, we'll say from 0 to 3, is the distance we traveled. So we started at 0 meters and went up to 3 meters. And then we're going to divide it by the number of seconds it took, right? Divide it by the time. We started at 0 seconds and it took 3 seconds. So we are traveling at 1 meter per second. Great. We happen to notice on this orange line, the slope of this line is 1, and that's not an accident, right? Let's look at a different section of the graph. If we go from this point to this point, from 6.3 to 7.1, so from 6 seconds to 7 seconds. The distance we traveled is we started at 3 meters away and we ended at 1 meter away. So we traveled 2 meters. And it only took us 1 second. We started at 6 seconds and ended at 7 seconds. So this is 2 meters per second. This is some riveting division, y'all. And we noticed that this slope was -2. So our rate, we're traveling at 2 meters per second, but notice that this is backwards. We're headed towards the house or towards the origin point, which makes sense that the negative slope would correspond to walking backwards. And then just for some fun, let's talk about when we've got a horizontal line, that's a slope of 0. So our speed is 0, which is great because we've decided that horizontal lines is when we're stopped, which is when our speed is 0. And then the last one I want to highlight here is if I had asked you, or if we had wanted to discuss what's the speed here. We know how to find the slope of straight lines. We're pretty good at that by now. But the slope of a parabola is not something we've really talked about yet. And that's where calculus comes in, right? Finding the slope of a parabola, you'll use the derivative. And that's something we'll learn in Unit 3. I'm pretty sure it's Unit 3. Cool. So in a nutshell, if you have a distance graph and you want the speed, we're going to use the slope to find the speed. All right. Let us go now to if we have a speed graph and we want the distance traveled. All right. So again, we've got hours, so time on our x-axis. We've got miles per hour, which is a speed on our y-axis. We've got our equation, distance equals rate times time. We've solved for distance because it's what we want. The equation has rate times time because it's what we have. Lovely. All right, so if we want the speed, if we want the distance traveled in the first 2 hours, right, just from here to here. If we want the distance traveled, we do the rate times the time. We know the time is 2 hours just because we wanted it to be from 0 to 2. And we know the rate, it's a flat rate. It's 30 at every point. So, and this makes sense, right? If you're going 30 miles an hour and you drive for 2 hours, it's going to be 60 miles. You're going to travel 60 miles. Let me erase this equal sign. And let me move my face. Hey, from the left. Cool. So the thing I want to note physically over here, like the physicality was we're finding the slope when we're doing these this equation, like because it's rise over run is the slope of this graph. Over here, the physicality is a little different, right? When we do 30 times 2, and we're talking about this orange portion of the graph now, the 30 is like the height, the 2 is the base, and when we multiply base times height, we're finding the area underneath this graph. So when we're using the rate and the time to find the distance, the physicality, the graphical thing we're doing is we're finding the area between the x-axis and our curve, our line. So distance traveled, we use area. Let's try another part. So if we have this straight line, that's just terrible, guys. If we want to find the distance traveled from the second to the third hour of our trip, so we're starting at hour 2 and we're ending at hour 3, how much did we travel if our speed dropped down from 30 to 0? You know, like if we had to stop at a stoplight, say. The way we're going to do that is we're going to find the area underneath this curve from x equals 2 to x equals 3. And so it's going to look like this triangle bit. Our equation isn't like perfect anymore because our rate is changing. We can't just plug in a number. So what we're going to do instead is say the distance is the area of that triangle. And the area of a triangle is 1/2 base times height. The base here is 1. The height here is 30. So we traveled 15 miles from the second hour to the third hour. Cool. And now we look to the future and we say, okay, what about this part, right? So in geometry, we definitely learned how to find the area of rectangles. We learned how to find the area of triangles. We learned how to find the area of a lot of shapes, but we didn't learn how to find the area underneath a parabola, right? Maybe we could approximate it with like different circles. Maybe we could approximate it with rectangles. But if we want the like exact area, we're going to need something called the integral. And that's unit 4. This is kind of like the heavy hitters of like why is calculus, like what can you do with the tools we'll learn in calculus. You can find the slope at any point of a line, which in one instance is useful for finding speeds. And we can also find the area underneath curves, which again has many uses, but one of the main ones is if we're given speed, we can find distance. All right, that's in a nutshell what I wanted to get across at the end of class today. All right, guys, if you have any more questions, email me, message me on Teams, reach out. Thanks.